Hi there. Today we'll be looking at a question from the IBHL physics course, in particular, a question relating to nuclear physics. So the question is that a reaction takes place in the core of a particular nuclear reactor. The reaction is as follows. Uranium-235 plus X, a particle which we will later find, produces barium-144 plus krypton-89, the same krypton, it's named after the same planet from Superman came from, plus 3x, the same x as referenced earlier. Now here's some details about the nuclear power plant. The nuclear reactor, inside the nuclear reactor, there are 9.5 times 10 to the power of 19 fissions that takes place every second. Each fission reaction gives rise to 200 mega electron volts of energy that is available for the conversion of electrical energy. And the overall efficiency of the nuclear power plant is given as 32%. Now let's try to solve the first question. Important thing to note in this sort of question, which is from paper 2, there's multiple different sub-questions. So it's important to read the core message before one moves on. So question AI states, it asks, state the name of the particle X and its nature. So we know that since it's a nuclear fission reaction, as uranium-235 is involved, it must be a neutron. And the nature it's referring to is its mass number, so 1. So you write N with 1 as its mass number. Question AII asks, state one form of energy that is instantaneously released in the reaction. So there's multiple correct answers in this, right? You can use kinetic energy because that, as the particles get energized, they move faster, right? Or you can use gamma radiation because radiation is released, and you know gamma, which falls under the EM spectrum, is comprised of these small pockets of energy called photons. And lastly, you can use binding energy, which forms the heart of all nuclear science, using Einstein's famous equation of E equals to mc squared. Okay, now let's move on to question BI. Determining the mass of the uranium-235 that undergoes fission in the reactor every day. So to begin with, let's absorb in some of the information that was earlier given, and let's solve this methodically. First thing we want to do is, how many fission reactions takes place every day, right? So that can be calculated by using the equation 9.5 times 10 to the power of 19, because you've been given that's the number of fissions per second, times 24 relating to the hours, times 3,600. That takes into account the seconds and the minutes. This gives us the result of 8.2 times 10 to the power of 24 fission reactions each day. Okay? Now we have to find out the mass of the uranium from the core that gets used every day, right? Sorry, the mass of the uranium atom, actually. Let's do that first. The mass of the uranium atom is calculated by using the uranium mass number, 235, times it by 1.661 times 10 to the power of negative 27. That 1.661 times 10 to the power of negative 27 is the atomic mass unit, U, which you will find in your data and formula booklet, giving the mass of uranium atom as 3.9 times 10 to the power of negative 25 kilograms. Finally, moving on to the mass of uranium used each day, we can combine these two results to find the overall answer. So we use the total, we use 8.2 times 10 to the power of 24, i.e. the number of fissions in a day, times 3.9 times 10 to the power of 25, i.e. the number of uranium atoms, use the mass of the uranium atom to find the total uranium weight per day, which comes down to 3.2 kilograms. Not bad, huh? Clearly highlighting the high energy density within uranium. Now let's move on to question BII, which asks us to calculate the power output of the nuclear power station. So in here, remember, you have to use some of the information that was provided to us earlier, right? So let's begin with energy per fission. You know that you've been told it's 200 mega, so 200 times 10 to the power of 6 electron volts. So let's convert that into energy. So that's 1.6 times 10 to the power of negative 19. So you get the energy per fission in joules as 3.2 times 10 to the power of negative 11. Look, it's always important to, it helps converting everything into joule, because electron volt isn't like a nice unit for energy that we normally associate with power plants, therefore much smaller values. Now, to find the total power output of the power plant, we have to take into account the efficiency of the power plant. So we have 9.5 times 10 to the power of 19, the number of fissions per second, times 3.2 times 10 to the power of negative 11, which looks at energy per fission, so you have total energy there produced per second, times 0.32, i.e. the efficiency. So you get the total power as 9.7 times 10 to the power of 8. Thank you for watching. Hope this video was useful.